Hello, today we are going to talk about active elements. We've studied passive elements such as resistors, capacitors, and inductors. Now we're going to study diodes and transistors, which are elements that let us control systems by the actuation and turning the parts of the element on and off. So in order to study the diode and transistor and other active elements, we're gonna first of all learn how they operate and why they are so useful. So the objectives the objectives are to be able to identify the modes of operation of different transistors, conceptualize the physical behavior of transistors, and be able to predict the circuit response using transistors. Let's talk about passive elements. We've talked about resistors and capacitors and inductors, and now we're going to talk about diodes. So passive elements cannot be controlled by another electrical signal. They depend on their own properties, on their own material. So they depend on their nominal value. For instance, a 100 kilo ohm resistor will have a response that is linear, where we have V equals IR based on Ohm's law. And basically, the resistor will give us a relationship between the voltage and the current. The larger the nominal value, the larger the resistance, the smaller the current. Capacitors have a similar scenario where the units of farads, we want to have capacitors with large capacitance if we want to be able to provide a large amount of charge, or we want to have a small capacitance if we don't need a lot of charge to start with. Inductors have a similar behavior. They are also passive elements with units of henries, and we can build configurations with inductance or with inductors to create transformers and other magnetic fields, such as motors, etc., where depending on the value of the inductance, we will obtain a specific response. Diodes are a new element that we'll talk about, and they're extremely useful because they protect the circuit and allow us to enforce direction of the current. So the key points are that passive components cannot be controlled by another electrical signal and do not require an external power source. Active components, on the other hand, such as transistors, do require an output signal to help us control the system, and most likely will require a power source. So as we mentioned, passive elements build passive circuits. So a passive circuit contains only passive components. So common RLC with resistance, inductor, and capacitors. This is a passive circuit that is very common for controlling the voltage peak to peak, or to trim a signal to clear the noise, etc. These are passive circuits that are very useful but cannot control the start or stop or ending time or a change of velocity, which change of signals that we will have with a microcontroller or with transistors. This is a rule of efficiency. Um, Power output is going to be less than power input. This is not the case with transistors, and we'll talk about that. There's a gain when you have with amplifiers, for example, that the power output could be amplified. But with passive circuits, there's an efficiency that will be computed based on the power in and the power out, right? So passive circuits and passive systems will have this efficiency or this rule where power output is going to be less, or in best case, equal to power input. Now, active components are transistors and amplifiers. And key points are that they can control the current based on an electrical signal. So you can use a power source or an electrical or voltage input to control the passage or the actuation of the circuit. They require an external power source, and they do amplify, or they can amplify, electrical signals. For this case, there's something called gain, and this is one of the ratings of the transistor element. And the gain is there to show that the power output can be larger than the power input at certain operational points. So, in other words, active circuits contain at least one active component, the same way that we said passive circuits can only have passive components. An active circuit, kind of like microcontroller, need to have at least one active component. So either a transistor or an amplifier. For instance, a smartphone is an active circuit because it has millions of transistors. And there's technology to create transistors that are as thin as a human hair. And there are transistors that are as big as a thumb. Those transistors are the ones that you put on a breadboard, for instance. But Intel and other AMD and other companies that have the resources create very, very, very small transistors so that can be placed in electronics. In fact, the active circuit can be called electronic. So when we talk about electronics, we're talking about circuits with active elements. We mentioned before that there are three main types of elements. And when you go to the periodic table, you would have what is called the metals, the transition metals, and the non-metals, and ideal gases, or not ideal gases, but noble gases. And the broader or the general grouping of elements are usually done in three groups: the conducting type, the insulating type, and the semiconductors. So conductors are, when you have a circuit, for instance, you would have your battery, and you have a resistor, and say you have a capacitor. Okay, and then of course you have your ground. So talking about a passive circuit, resistors can made out of non-metal or like carbon, for instance. So they, in a way, they're a non-metal, therefore they're not conducting materials. And capacitors can be an insulator, such as barium titanate or PZT or lead zirconium. But the wires between the elements are conducting materials to be able to conduct the electrons. So the electrons are flowing through these wires that are usually made of copper or silver. For very advanced electronics, such as some parts of your computer, you can even have gold, etc. So the conductors, such as gold and copper, allow the flow of electrons. Insulators prevent the flow of electrons, and some insulators are designed to get polarized, such as capacitors, but in general, plastics and rubber do not allow the flow of electrons. In fact, resistors prevent the flow of electrons to flow freely, but not as evident or not as strong resistance as a capacitor, but they still prevent flow conduction of electrons. Now, semiconductors are a group of materials that are in between, that they're not 100% insulating, but they're not 100% conducting materials. A very common semiconductor material is silicon, and this is very famous because it's used in electronics for active elements and for their manufacturing capability. So it's easy to be manufactured and easy to be collected, and it's not too expensive. So any computer, any electronics will have parts are made out of silicon. Now, diodes are a type of semiconductor materials or a type of passive element that is fabricated with semiconductor materials. So when you build, or again, when you have a semiconductor, you can have, they're divided into groups, what is called the positive type or the P type and the N type. The positive type, P for positive, N for negative. But in short, they're used or they are known as P type and N type. Yet diode has um, fabrication or is fabricated with this conjunction of two semiconductor materials, the P type and the N type. And the difference between the P type and the N type is that N type has material with an extra electron that it can give to the P type. So when it's electrified, the material with with the extra electron lets the electron flow to the material without the electron. So in other words, P type, say P type has one extra ion, N type has is missing an ion. So when there's a current, the extra ion from the P type is moved to the N type because it's missing an ion and they want to be stable conditions. Okay, so a diode does exactly that part. Combines semiconducting materials in such way that, say, silicon and phosphorus, such that whenever there's current going through the diode, there's going to be able to flow in this direction, left to right. But whenever there's current on the opposite direction, if you think about a sinusoidal wave or AC current, the current cannot flow on the opposite direction. So this is very useful because this is how you implement circuits in AC applications where you can only allow current and voltage to flow in certain directions. So when you buy a diode, it will come with a long leg and a short leg. We'll see these later in the lab. The diode has a short leg and a long leg so that the operator or the engineer knows how to install the diode in the circuit. So the long leg is the anode and the left leg is the cathode. Okay, so you have to install it in the way that you want to have your current flowing because the current will not flow the opposite way. That's why when you see the diode on a circuit, you will have this line vertical blocking the flow of electricity because current can only flow in the direction of the triangle. When you talk about diodes, you will hear something called forward biased current or forward biased voltage. That is the name of the current and the voltage that goes through. In other words, is the voltage and the current that is flowing in the direction of the triangle. Because, as we just mentioned, current and voltage cannot go the other way around, even if this is a sinusoidal wave. So to distinguish with which current and voltage we're talking about, we're gonna say forward bias. So the forward bias current is the current that can go through the diode in the right direction of the element. If we take a look at the current versus voltage graph, we can see that it's highly nonlinear. So even there's a passive element, Because if you compare, again, if you compare to a resistor, when we have voltage equals IR, we know that the relationship between the voltage and the current is given by R as a straight line. Of course, at some point it's going to be a breakdown voltage, but there's a operation point that is a straight line. For a diode, that doesn't happen. So if you have a circuit where you have your diode, and let's say you have a resistor and a battery, and you have forward current, it will start increasing exponentially at a very small voltage. So at a very small, we'll see what this voltage is. At this voltage, you will have current that will increase exponentially. But if you try to reverse this direction of the current, this will not happen. This will act like an open circuit, and there will not be flow of current through the circuit, but it will be a little bit of reverse current through the diode, and this will happen in a voltage plot where this operational value, and then you have the breakdown current where the element breaks. So that's another thing you have to be careful, is that you size your diode for your specific operation. If it's 3.3 volts, then of course it's going to be a different diode than if you put through a circuit of 120 volts. So you have to be careful because they do have a breaking point, because the current can increase exponentially. For silicon diodes, remember that diodes can be, you have the N-type and the P-type, and silicon is very common. So, but you can also use different materials. There's research. Companies are always finding cheaper materials that will have better performance. But in general, diodes using silicon, which is very common, will have activation voltage or forward voltage of 0.7 volts. So it's also called VF. When you buy a diode, the specification page will bring something called VF, which will be the forward voltage at which this means that there's a minimum of 0.7 volts needed to let current go through. And as we mentioned before, the current will increase exponentially after a very small increase in voltage. But you have to meet the requirement of the VF voltage to let any current go through the diode. When you size or when you need to buy a diode, the three main characteristics that you have to look for are the forward bias, the forward voltage, which is the voltage at which the diode activates, the breakdown voltage. If you remember in a curve of voltage and current, you have this breakdown voltage and this the forward voltage. So this was 0.7 volts for a silicon diode, and the breakdown voltage is where it will break, trying to prevent the current to go on reverse mode. So these three things are shown on specifications by manufacturers. So when you buy a diode or when you're planning to buy a diode, you have to know your forward voltage, that if it's not silicon, it's going to be something else. Your breakdown voltage, which will be this value here, where it's going to break, it's not going to function anymore, and it will not protect the circuit anymore. And the maximum forward current. That is the maximum current that it will allow before it breaks. So those three things are the main characteristics of a diode that you have to look for when you buy one. Now, the two most common applications of diodes are for circuit protection, so you don't allow any back current into the system, and for rectifiers. Rectifiers are circuits that let you convert AC signals into DC signals. So for instance, the converter or the plug from, if you look at your computer, there's the plug that goes to the wall, and this is 120 volts AC. And then that plug will go into looking at top view, that will go to your wall, but there's a cable that goes to a rectangular box. The rectifiers are in here because the computer, your laptop, takes DC voltage and current, but you're connecting your laptop to charge the battery to the wall. So the rectifiers are in here, and they look like this. They're a board, they're a circuit where a configuration of diodes that allow the signal to be rectified. And the principle of rectifying a signal is when you have your 120 volts AC at 60 hertz, by using a rectifier, you can eliminate all the negative voltage. Because if you remember, the diode will have this prevention of backflow of current. Aside from rectifiers, the other very common application of diodes and very useful application of a diode is for protection or reverse protection diode. That's the name, where you have your power source right here, all your circuit with capacitors and resistors and with inductors, and you have all your power source. But say this is your control board. So this is where you have your controller, this is where you have your sensors, and they could be very expensive sensors. Like optical sensors could be $1,000 each. So it's very important that you have a way to use the sensor and not having to worry about burning the control system or the sensor every time you have unexpected values of current or voltage. So in this particular case, you would use a diode. When the current is flowing normally, then you have the values of current and voltage that you want. Remember, to let this happen, to let this current happen, you have to provide a voltage that is greater than your forward bias voltage, which is 0.7 volts. So you need more than that. And for instance, if this is supposed to be operating at 3.3 volts DC, if you apply, if you provide, this is a thing that I want to make sure I mention right now. If your battery is providing 3.3, okay, from your source, so it's a 3.3 volt battery, then this is not going to be enough to operate your sensor, so you're going to have issues reading your full scale, because in order to get this voltage through, you need 0.7. So what you end up having here is, by conservation of charge, is 3.3 minus 0.7, okay? And of course this is going to be 2.6 volts. So that's why when you read your voltage with a multimeter at certain parts of the circuit after the diode, your voltage is going to be less than the power source. So in that case, you need to tune your circuit to be having higher voltage. And in this case, if what you need to supply is 3.3 here, then you need to be applying at least 4 volts. LEDs are a type of diode that, LED first of all means light emitting diode, and they're this type of diode that when the electrons go through the element, they flash light. So they're a very interesting type of semiconductor where the schematic symbol is this. It's just a diode with arrows pointing out, symbolizing the light going through or producing light. And light emitting diodes are the opposite of something called photodetectors. So photodetectors are diodes that have arrows pointing in, and they can detect light and by an impulsing current. So LEDs have the characteristic of being able to emit light, and photo detectors, I'm sorry if this is not clear, detectors are used as sensors to be able to detect light intensity or light pulses, etc. Other types of diodes are the Zener diode and the Schottky diode. These type of diodes are particular diodes because they do have reverse voltage nominal value. So they're used for protecting circuits from power surges. And a common example, for instance, is if you have a 6-volt battery connected to a resistor that is 100 ohm, for example, you have a Zener diode connected to your ground, and then you have here your load, which could be a control system or sensors, etc. Then if you're using the 5.1V, this means that it's 5.1 voltage reverse current, reverse voltage. Therefore, 6 minus 5.1 is 0.9. So 0.9 volts are going through this upper side of the circuit, meaning that V equals IR from Ohm's law, only a current of 90 milliamps will flow through this upper side of the circuit to the load. So this particular setup for using the Zener diode will protect the current going into, or will restrict the current going into your controller or your particular load.